This is an IB Physics video about charge and potential. So we know that current can be defined as the rate of flow of charge. How much charge is passing a certain point every second or every unit time. So when we're inside a wire, imagine a cylindrical wire there, and inside there's lots of electrons. Remembering that if the electrons are flowing to the right, then the current is flowing to the left because it's conventional current. And if the current is the rate of flow of charge, then we can figure out how fast those charges are flowing, because we can think about if this wire has an area of A. That's the area there, and the current, let's say, is moving with a velocity v. Then we have the total volume of electrons, which are moving in 1 second, because velocity is meters per second. The total volume of electrons that are moving in 1 second is v times a, the velocity, the distance per unit time, times the area. So you've got the total volume of electrons that are moving in 1 second. So volume per second is v times a, and then you also have the total amount of charge. Now, the total amount of charge is the number of charges, number of electrons in that unit volume, the charge, the number of charges per unit volume, times however many charges, however much charge in coulombs they have. So that's the total charge per unit volume. So therefore, the current, the rate of flow of charge, is how many of those charges, the total number of charge, how much charge is flowing per second. So if this is total charge per unit volume, and this is total volume per unit time, then by multiplying those two together, we get the total charge per second, which is the current. So we end up with NQVA, or as it is in your data booklet, I equals NAVQ. So this gives us a value of figuring out either how fast charge carriers are moving within a material, or the dimensions of the wire, or the current that would be flowing when the charge carriers were flowing at a particular speed. Imagine you've got a charge, this charge here on the left side here. That charge has an electric field around it, and then you get another charge, a second charge, this pink one on the right here, and you want to move that. Let's say it's infinitely far away at the moment, so it's nowhere near this charge. It is not under the influence of that electric field. It's nowhere near the blue charge. It's not under the influence of that electric field. Let's say you want to move it closer. Well, if you want to move this charge to this point here, then you're going to have to do some work, because these are both positive charges. They're repelling each other, so you're going to have to do some work. You're going to have to put in some energy to move it along that line. So you're going to have to do some work to get it from infinity to a point in the electric field. Now, if this was a point unit charge, we define that as the potential. So potential is the work done moving a point unit charge from infinity to a point in an electric field. So now imagine that you're going to move another charge, in exactly the same point unit charge, from the same place at infinity all the way to a slightly different place in the field. There. That's going to take a different amount of work because you're moving it to a different place. And so there's a difference in the amount of work between this point and this point. A change in work, a difference in the work done to get to those 2 points. Now, if each one of those values of work is called the potential, then that difference in work is the potential difference. And we've got a symbol for potential difference, V, otherwise known as voltage. So the voltage, or the potential difference, is the difference in the amount of energy that a unit charge has at a particular point in an electric field. So we're talking about work done per unit charge. So voltage is the difference in the work done per unit charge. So voltage, or potential difference, is work done per unit charge. So it would be the work done moving from this pink circle here to this purple circle here. That would take a certain amount of work, and the work done per unit charge moving from there to there would be the potential difference. That would be the voltage there. What we can then say is that, well, if V equals W over Q, voltage potential difference is work done per unit charge, then the amount of work that you do, or the energy changed, is V times Q. Now, if the energy changed is V times Q, then we know that power is energy change over time, so VQ over T. So you have another equation for power. So if you're moving stuff around, remember that QT is current. So we already know that P equals IV, so that works. So then if you're moving electrons around, or you're accelerating a particular amount of charge, then if you take an electron, we know the charge that an electron has. So we know what Q is. And so if we accelerate through a potential difference of 1 volt, if we accelerate an electron with minus 1.6 times 10 to the minus 19 coulombs of charge, then we get a certain amount of energy. It takes a certain amount of, we give that electron a certain amount of energy. So if we accelerate 1 electron through an electric field of 1 volt, then that will have a certain amount of energy, always the same amount of energy each time, because the electron will have the same charge each time and the 1 volt is the same each time. And we know that the charge on an electron is minus 1.6 times 10 to the minus 19. So that gives us an amount of energy that's always the same, 1.6 times 10 to the minus 19 joules of energy. 1 volt, the charge on 1 electron, so 1.6 times 10 to the minus 19 joules of energy. Now there's no negative sign there because energy is a scalar. So this unit here is a much more useful, when we're talking about these tiny particles, it's a much more useful amount of energy to deal with than the joule, because it's much smaller, and so it's more, there's fewer orders of magnitude difference between the unit itself and the amounts of energy that we're dealing with. So we often use this when we're talking about particles, and this is called an electron volt, or EV. So this unit here is often used when we're talking about energy on an atomic scale.